So looking at part A here, we're going to rank the brightness of the bulbs using our model for current, voltage, and resistance. So I added arrows here showing where the current's going to travel in the circuit. So we have the current coming from the battery, splitting down the right branch, the left branch, the current splitting at this small parallel section, then coming back through C and back to the battery. Just by looking at this, we should see that C is going to be the brightest. So the current leaving the battery has to go back in, and C is the last bulb in the line to the battery. So C is receiving 100% of the battery's current. D and E are going to be equal because in a parallel branch the current splits evenly here. So D and E are going to have the same amount of current, thus the same brightness. We're going to have A and B, which are going to be equal to each other because they're in series with each other and they're in the left branch of this parallel section. So when comparing D and E, we see that since D and E equals each other, A and B are going to equal each other, but we don't know if this is going to be brighter or is this going to be brighter. We have to look at voltages and resistances as well, other than current. So in a parallel circuit, you have to have a voltage drop. The voltage drop going back to the battery has to be 0. And in a parallel section here, there's going to be less resistance. So we're going to have more than 50% of the current is going to go this way, and less than 50% of the current is going to go this way. So when looking at voltage drops and resistances, we can relate this to using Ohm's law. Voltage equals current times resistance. So we know that more current is going to go this way, and we know that less than 50% of the current is going to go this way. So D and E, the current splits here. There's going to be a smaller voltage drop here because even though they receive more current, these parallel has less resistance. So A and B is going to be brighter than D and E because even though they receive less than 50% of the current, they're in series with each other and they have to have the same voltage drop. So A and B will be brighter than D and E. However, we have F here. F will have a higher voltage drop than A and B because there wasn't a huge voltage drop here, but to make up for this small voltage drop, we need a larger voltage drop at the end of this branch. Thus, F will be larger than A and B because A and B are going to be the same. All right, so now we are going to find the equivalent resistance of the entire circuit if each one of the bulbs is 6 ohms, and then we're going to calculate the current produced by the battery. All right, so here's the circuit diagram here. The way I like to find equivalent resistances is to take care of the internal parallel sections first, and then you're going to combine the series, and then what's ever left, you're just going to add the series. Okay, so D and E is probably the best starting point. So we see that D and E are in parallel, and the equation for finding equivalent resistance. All right, so calculating the current produced from the battery is actually very simple once you have the equivalent resistance. So now we're just going to use Ohm's law. So V equals IR. In the circuit, it's given that the battery voltage is 20 volts. Then we're solving for the current, so we're solving for I. And R is what we just found over here, 78 over 7 ohms. We're going to divide that out. That cancels. And if we do the math here, we will find that the current produced by the battery comes out to be 1.795 amps. Okay, so problem B.75, we are going to write Kirchhoff's current law for junction 1. This right here is defined as junction 1 in the problem. And then we're going to write Kirchhoff's voltage loop rule for the loop battery ABC. Battery A, B, and C. So, starting with Kirchhoff's current law, that basically states all current entering the junction has to equal the same amount of current entering the exiting the junction. So the current coming in, that's current from the battery, so I battery. And coming out, we have the right and the left. If we add the right and left together, we will get this. So this is just going to be current right plus current left. So this is what our KCL is. And then we are going to write Kirchhoff's voltage loop rule for battery ABC. Okay, so we are neglecting this entire side of the circuit. We're only going to worry about this loop right here. So Kirchhoff's voltage loop rule, you basically go around the loop and you start at the battery, and then you want to end up at 0. So the whole equation has to equal 0. So what we're going to do, we're going to start at the battery. I start at negative 20 volts. Now if you look at Ohm's law, V equals IR, we're looking for voltages. So we don't necessarily have the voltages for A and B yet, or C, but we have the resistance, and we have our variable defined as the current going on the left branch. So we are going to, since we're starting at negative 20 volts, we're going to just go up from here. So we have 6 ohms times IL, and then that's for bulb A. Now we're going to do bulb B, which is also 6 ohms times IL. And now C is going to be different because in this circuit, C has 100% of the battery's current. So C is going to have I battery. And we already calculated this to be 1.795. So what we're going to do is 1.795 times 6 ohms. And all of this is going to equal 0. So this is Kirchhoff's loop rule. As you travel around the circuit, the voltages basically have to drop or add up to equal 0 at the end. Okay, so now we're on the last part of the problem. Find the current through and voltage across bulb F. F is right here. So we modeled these equations, I battery is I left plus I right. We need the current on the right branch, because if you look closely, the current through F is just going to be the current down the right branch. Even though it splits here, the current's going to equally split to both sides here down the right branch, and then it's going to come together right before F. So F is just going to be I right, the current, I mean. So we don't have I right, but we can solve for I left, and we have I battery. So if we solve this equation that we already have for I left, let's solve this real quick. So IL times 12 ohms plus, this comes out to 10.77 volts equals 0. We can move 20 over here, then 10.77 over there, save some time because my phone is dying. IL 12 ohms plus, and this is just 9.23 on this side. If we divide it here, 12 ohms, IL will become 0.7691 amps. Now, this number here does make sense because we said in the beginning that more than 50% of the current is going to go this way and less than 50% is going to go this way. So we just solved for I left and we got 0.7691, and the total battery current is this. So I left is less than 50% of the total current. So we know we did that right earlier. So now we can use this, or we can use this equation to solve for I right with the current through F. So we have let's see, I battery, which is 1.795, 7691 plus I write, subtract this, subtract that, we find that I write comes out to be 1.0259 amps. So this is the current at F. Now we can use Ohm's law, V equals IR, to solve for the voltage at F. So we have the current at F, 1.0295 or 259, and we have already given that the bulb is 6 ohms. So we multiply the 1.0259 times the 6 ohms resistance, we get that the voltage at F comes out to be, let's see, that's 6.1554 volts. So that is the voltage at F. So we have the current at F, 1.0259 amps, and we have the voltage at F.